Stop using proxy-based load balancers for your internal TCP workloads right now. I just helped a team significantly cut their latency and eliminate a single point of failure by switching to GCP's internal pass-through load balancer, and I'm going to show you exactly why this architecture matters.
Hey everyone, welcome back to the Network Ninja Cloudcast. I'm excited about this one because I've been confused about when to use pass-through versus proxy load balancers.
Perfect timing then. Today we're diving deep into GCP's TCP/UDP internal pass-through load balancer, specifically why its architecture is fundamentally different and when you absolutely need it.
So what's the actual problem with regular internal load balancers? I've been using them and things seem fine.
Here's the issue. With a proxy-based load balancer, every single packet goes through the load balancer itself. Your client sends traffic to the load balancer terminates that connection, then opens a new connection to your backend. That means the load balancer sees every byte of data, and your backend servers only see the load balancer's IP address as the source.
Wait, so my backend can't see the real client IP? That seems like a problem for logging and security.
Exactly. And here's where the internal pass-through load balancer is completely different. It uses what Google calls maglev technology under the hood, and it doesn't proxy traffic at all. Instead, it distributes traffic directly to your backend VMs using a software-defined networking approach. The load balancer is essentially a distributed system built into Google's Andromeda virtual network, not a single appliance sitting in the path.
Okay, I need an analogy here. How does pass-through actually work if there's no middleman handling the traffic?
Think of it like a smart traffic light system versus a toll booth. A proxy load balancer is the toll booth. Every car stops, pays, and the toll booth decides which lane to send you to. The internal pass-through load balancer is more like an intelligent traffic light network. The lights are coordinated across the entire city, they know where traffic needs to go, and they direct cars without ever stopping them. The cars flow directly to their destination, but the traffic system still controls the distribution.
So the traffic goes directly from my client VM to the backend VM, but something is still making the load balancing decision?
Precisely. The load balancing decision happens at the network layer through Google's SDN. When a client VM sends a packet to the load balancer's internal IP address, let's say 10.128.0.100, Google's network fabric intercepts that packet and forwards it directly to one of your healthy backend VMs. The backend VM receives the packet with the original source IP intact, processes it, and sends the response directly back to the client.
That's huge for logging. But wait, you mentioned TCP and UDP. Does it work the same for both?
Great question. Yes, this load balancer operates at layer 4, so it handles both TCP and UDP traffic. By default, it uses 5-tuple hashing for packet distribution. That's source IP, source port, destination IP, destination port, and protocol. This ensures packets from the same connection always go to the same backend. Now, if you want to control how new connections from the same client are handled, that's where session affinity comes in as a separate configuration. You can set options like client_IP or client_IP_port_proto to influence that behavior.
What are the actual use cases where I'd choose this over the internal HTTP load balancer?
3 main scenarios. First, any non-HTTP protocol. If you're running MySQL on port 3306, Redis on 6379, or custom TCP services, you need this. The internal HTTP load balancer only handles HTTP and HTTPS. Second, when you need the original client IP preserved without any header manipulation. Some legacy applications or security tools require seeing the true source. Third, UDP workloads like DNS servers, gaming backends, or VoIP systems.
What about the common mistakes? I'm sure people mess this up.
The biggest mistake I see is forgetting about health check firewall rules. The internal pass-through load balancer supports all the same health check protocols as other GCP load balancers, including HTTP, HTTPS, TCP, SSL, and gRPC. The key thing to understand is that health checks are always out of band, meaning they're separate from your actual user traffic. People configure the load balancer, forget the health check firewall rules, and wonder why traffic isn't flowing. You need to allow traffic from the health check ranges, specifically 35.191.0.0 out of 16 and 130.211.0.0 out of 22.
Oh, that's a gotcha. Any other pitfalls?
Yes, understanding the regional versus global options. The internal pass-through load balancer is regional, meaning backends must be in the same region as the load balancer's forwarding rule. Now, it does support a global access setting, which allows clients from other regions to reach your regional load balancer. But that's different from having backends in multiple regions. If you actually need to distribute traffic to backends across multiple regions, you'd need the cross-region internal application load balancer, which is a distinct product designed for that use case.
Let me make sure I've got this. The internal pass-through load balancer doesn't actually touch my traffic. It uses Google's network magic to direct packets straight to backends, preserving the original source IP. It works for any TCP or UDP protocol, not just HTTP, and it's regional but can accept traffic from clients in other regions with global access enabled.
Perfect summary. And here's your pro tip. When you're designing internal microservices that need to communicate over non-HTTP protocols, this is your go-to. It adds minimal latency overhead compared to proxy-based solutions because there's no proxy hop, just some lightweight SDN processing, and it scales automatically with Google's infrastructure.
This makes so much more sense now. I was treating all load balancers the same, but the architecture is fundamentally different.
That's it for today's episode. If you found this helpful, please hit that like button and subscribe to the channel.
And share this with anyone building internal services on GCP who might be using the wrong load balancer type.
Thanks for watching the Network Ninja Cloudcast. See you in the next one.